Hello students, welcome back. We are done with part A of the problems, 1A and 2A. As a matter of fact, we did a lot more than what we have over there. We did it in far more complicated setting, so much that 1C and 2C are covered as well. Basically, this is just one application of multiplication rule. So first times a second. This one is two applications of multiplication rule. First row times the second row times the third row. Same goes to this guy as well, with versus without replacement. In this worksheet, we did 2 rows, 3 rows, and then 4 rows as well. So we did far more than those. Let's go to problems B, 1B and 2B. That's a little bit different. If two balls are selected without replacement, what is the probability that we get one red and one blue in any order? One red and one blue, so it can be red-blue or blue-red. Let's consider that. So if 4 balls are selected without replacement, what is the probability that the first ball is, this is way too complicated. Let's go back to 2 balls. No, down here. If 2 balls are selected without replacement, what is the probability that we get one red, one blue in any order? Okay, one red, one blue. So we're talking about this probability of getting red in my first draw and then blue in my second draw, or blue in my first draw and then red in my second draw. That's basically it. So in any order it says, so we have red first and then blue, or that's or plus or first blue, second red. That's basically it. So we have to use multiplication rule for this part, also that part, but then again we have to use addition rule to add them up. So how does this probability, first probability works? So I have 6 out of 10, 15, excuse me, I changed the numbers, right? And then 5 out of 14, that's red and then blue. And then blue and then red. I mistyped it over here. First draw, I'm drawing out of total 15 balls. Second draw, I'm drawing out of 14 balls. So if I add them all up, then I'm going to cover one red and one blue in any order. Red-blue or blue-red. Make sense? Let's make it a little bit harder. Let's go one step further. Let's do it this way. If 3 balls are selected without replacement, all right, what is the probability that we get 1 red and 2 blue balls? Let's do it this way. 1 red and 2 blue balls. So red, blue, blue. So red, blue, blue. Or blue, red, blue. That's a second possibility. Or blue, blue, red. Did I cover everything? Blue, blue, red. Did I cover everything? So this time I made it a little bit harder. 3 balls are selected, and then we want 1 red and 2 blue balls. So red, blue, blue, or blue, red, blue, or blue, blue, red. Are there any more other possibilities of arranging these colors? No, there aren't. And then we're going to come back and talk about this in a little bit more detail in part D. Okay, so those 3. So let's consider this part. Red, blue, blue, red 6/15, and then blue 5/14, and then next 4/13. Is everybody comfortable with these reductions here? I selected my first ball out of total 15 balls, so the total went down to 14 in my second draw, and the 2 balls are out, so in my third draw, total is down to 13. Now, red ball, they're total 6. Blue ball, they were total 5, and then by the time I take another blue ball, now the number of blue balls I can choose from is dropped to 4 because I started from 5. Next, blue, red, blue. Blue, 5/15, red, 6/14, all right. And then blue again, so I have 4/13. Does it make sense? Same idea, the number of balls dropping. And then now 5/15 for blue, and then 4/14 for blue, and 6/13 for red. That's the third possibility. Make sense? So if you add them up, then you're going to get this. But let's make one further observation here. Please note that each individual here is the same. They're all the same to each other. Why? The denominator is 15, 14, 13, and the numerator is 6, 5, 4 in different order, but multiplication is commutative. So each probability here, there are 3 of them, but each one is identical to each other. So there are total 3 times these. And that's going to be the answer. And then calculating this, of course, is left to the students. Does it make sense? So we are doing problem number 1 repeatedly, but 3 times. Why 3 times? Because getting 1 red and 2 blue, there are 3 possible arrangements. Now, if you have 10 balls to choose from, and then 4 red and then 6 blue or things like that, then things are far more complicated. How to arrange them? Or how about 3 colors? Choose 10 balls and 4 red and then 4 blue and 2 green. Far more complicated. But we have to start from somewhere, and starting point is rather simple case. So first, we can consider each individual probability using multiplication rules, and then we can add them up. But please note that each individual probability is the same, so we just multiply by the number of arrangements. Now this is without replacement case. What if we do the same thing with replacement? So I'm selecting 3 balls with replacement, and 1 red and 2 blue balls. Same setting. And how does this thing work? Well, this time I'm having it with replacement, so the number of total number of balls stay the same as 15. And then the color distribution again remains the same. So basically this is what we have. No reduction in denominator, just 15 all the way, and then no change in the probability for blue, and then each individual probability the same. Okay, that's even easier. Oops. Color part is a little bit screwed up here, sorry about that. Just a moment. Let me get the color back. Okay. Okay, why did I put 1 power even though what's first power will not change anything? Well, it reads kind of like this. 1 red, do you see this 1? And 2 blue. 1 red and 2 blue. And total, how many arrangements are there? Red, blue, 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 red, blue, 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 red. There are total 3 of them. So there are 3 possible arrangements. And then 1 red, 2 blue. And you can calculate this. So with replacement case is of course easier. Let's go back to without replacement case. A little bit harder because we have to drop the denominators by 1, and the numerators needs to be adjusted accordingly because we are talking about conditional probabilities. All right, they're all conditional. The second draw is under the condition what was selected from the first draw. But here, they are independent. Second draw, third draw, they are not related to previous draws. So same situation, same number of balls and same color distribution is repeated. Repeated multiplication of the same thing, that's why we have powers. Here, we use multiplication rule, yes, but they are not repeated multiplication of the same thing because they are not independent this time. So there's a relationship between, there's a subtle difference between without replacement versus with replacement. But in any case, I hope you can see that we have individual probability computation coming from multiplication rules. And then we have to have appropriate repetition for the arrangement. Arranging 1 red and 2 blue. Okay, the problem I gave you as homework, that's a heck of a lot easier as a matter of fact. Let's go back to that. I have only 1 red and 1 blue, so instead of 3 cases, I have just 2. Red, blue, blue, red. Just that. So twice of one, excuse me, I'm giving away a bit too much. We did this, so that's going to be sufficient for our homework problem. Now, problem number 3, no problem there. So I'll just leave you there. And we're going to talk about part D in a separate video.